Hey there, space enthusiasts! Get ready to blast off into the cosmos with us. Welcome to Spaceverse, where the universe is our playground and curiosity knows no bounds. Join us on an interstellar adventure as we dive into the depths of space, uncovering its mysteries and marvels. From the secrets of black holes to the landscapes of alien worlds, we're here to ignite your imagination and expand your cosmic horizons. With mind-blowing visuals, expert insights, and the thrill of exploration, Spaceverse is here to get to the ultimate cosmic journey. So strap in, hit that subscribe button, and let's embark on an epic voyage together into the vast unknown of Spaceverse. NASA announced on Thursday that Voyager 1 has achieved a historic milestone as the first human-made object to exit our solar system and enter interstellar space. Engineers at NASA working on the Voyager missions have been concerned about recent developments. Voyager 1 has been transmitting messages that have puzzled them for several months. The launch of the Delta rocket, aimed at exploring unseen physics in distant galaxies, marked a significant event. After over 45 years in space, NASA is now alerting the public to an unexpected discovery made by Voyager 1. What exactly has Voyager 1 found, and why is it so startling? Stay tuned for NASA's warning about Voyager 1's groundbreaking discovery after its 45-year journey through space. On August 25, 2012, an important record was quietly set, though it went largely unnoticed by the general public. For the first time in history, a human-made object crossed into interstellar space after traveling for 35 years and covering a distance of over 11 billion miles or more than 18 billion kilometers. This remarkable achievement belongs to Voyager 1, one of NASA's most cherished inventions. Interstellar space holds a special place in astronomy, existing as the vast expanse between stars. It's a realm where the solar winds, which are streams of highly charged particles emanating from the outer layers of the sun's atmosphere, cease to exert a significant influence on the cosmos. This transition occurs at a region known as the heliopause, where the solar wind from our sun collides with the winds from other stars. Essentially, it's the cold, expansive domain where the influence of neighboring stars becomes perceptible. Voyager 2, another human-made object, achieved the feat of crossing this boundary 6 years after Voyager 1. Voyager 1 accomplished this milestone by traveling at an astonishing speed of 37,000 miles per hour, equivalent to 325 million miles per year. To comprehend Voyager 1's current location, envision the heliosphere as a bubble shaped somewhat like a bullet surrounding the Sun. The Sun emits solar winds from its surface at speeds of approximately 1.79 million miles per hour. These hot, charged particles escape into space, creating a region filled with ionized gas known as helioplasma. However, these solar winds gradually decelerate and eventually come to a stop upon encountering interstellar space, where they mingle with denser, cooler plasma originating from particles formed during stellar explosions some 15 million years ago. The heliopause marks the practical boundary of our solar system. When the Voyager missions began in 1977, scientists believed the solar system's boundary lay just beyond Jupiter, about 365 million miles from Earth. However, they underestimated the extent of the sun's influence. One of Voyager 1's most surprising findings in interstellar space was its measurement of the density of the interstellar medium. According to the spacecraft's data, particles in this region were denser compared to the outer regions of the heliosphere. The plasma wave science instrument, which detects electron density through plasma wave vibrations, provided these measurements. Scientists initially expected Voyager 1's entry into interstellar space to be a straightforward event, but they discovered the boundary was much thicker and more complex than anticipated. This understanding was later confirmed when Voyager 2 also crossed the boundary 6 years later. The mission scientists were initially puzzled by the magnetic field data sent back by Voyager 1. They anticipated a distinct change where the sun's magnetic field encountered the interstellar magnetic field, but were surprised when the spacecraft detected no directional changes in the magnetic field. Voyager 1 has encountered a critical issue that has raised concerns about the continuation of its decades-long mission. While the spacecraft has faced challenges before, this current problem threatens its future. What exactly is troubling this celebrated figure in the world of astronomy? Voyager 1 is grappling with a memory malfunction. Memory problems might seem trivial on Earth, where forgetting is common and often harmless. However, for Voyager 1, located billions of miles away, this issue could potentially sever its connection with NASA forever. Over the past months, the space agency has been diligently troubleshooting the aging spacecraft, which began transmitting garbled data. This disruption prompted a halt in Voyager 1's scientific operations as engineers focused on diagnosing the problem. Their investigation has pinpointed a likely culprit, a single chip within the Flight Data Subsystem, or FDS. This component controls the telemetry modulation unit responsible for transmitting data to Earth. A breakthrough came when NASA engineers instructed Voyager 1 to send a readout of its FDS memory, revealing that approximately 3% of the memory had become corrupted, impairing the computer's functionality. Adding to the challenge is the spacecraft's age. Most devices are not engineered to operate beyond 50 years, and surviving in space's harsh environment is a testament to their durability. Compounding this issue is the fact that many of the original spacecraft engineers have passed away or moved on from the project, leaving behind a dwindling pool of expertise. This situation underscores the fragility and remarkable resilience of Voyager 1 as it continues its solitary journey through the cosmos. Diagnosing Voyager 1's current issue is compounded by its immense distance from Earth. Currently over 15 billion miles away, any signal sent to Voyager 1 takes approximately 22.5 hours to reach it, and the same delay occurs when the spacecraft responds. This delay turns troubleshooting into a slow-motion process akin to conducting a conversation where each party can only utter a single word per day. Engineers refer to this as troubleshooting in slow motion, making it challenging to pinpoint the exact problem. They speculate that the implicated chip may have been struck by a high-energy particle from space or simply worn out after more than 45 years of service. Adding to the frustration is that Voyager 1, based on the available data, cannot determine how to accurately transmit messages back to Earth. While the spacecraft continues to function as well as possible, its communication capabilities remain compromised. To tackle this issue, NASA enlisted the expertise of retired engineer Bob Rasmussen. Rasmussen began his career just before the Voyagers launched and had intermittently worked on the mission before retiring. However, the opportunity to troubleshoot issues with his old colleague brought him back. He had previously dealt with another communication problem the spacecraft had encountered and decided to stay on to address future challenges. Rasmussen and his team faced the daunting task of comprehending the spacecraft's intricacies. This involved meticulously reviewing the original design schematics, now yellowed and pinned to various walls, resembling an archaeological excavation more than engineering. In their diagnostic routine, engineers sent weekly commands to Voyager 1, typically on Fridays, and awaited responses by Sundays. The slow progress heightened frustration, yet they remained steadfast, including at the senior leadership level. A breakthrough occurred in March when analysis of a spacecraft response revealed a familiar string of numbers instead of the usual garbled message. This marked a pivotal moment tucked into the Rosetta Stone, with an engineer quickly deciphering Voyager 1's new communication pattern originating from its FDS memory. The next challenge was whether to accept Voyager 1's altered communication method or attempt to restore its original operational state. In the realm of space exploration, few missions rival the legendary status of Voyager 1 and Voyager 2. Launched almost 5 decades ago by NASA, these twin spacecraft were originally intended to explore the outermost planets and the boundary where the sun's influence ends. However, over the years, the Voyagers have significantly advanced humanity's understanding of deep space, surpassing expectations. Looking back at their launch, despite initial confusion over naming conventions, Voyager 2 was the first to launch. It departed from Cape Canaveral, Florida, on August 20, 1977, aboard a Titan Centaur rocket. Voyager 1 embarked on its own journey about 2 weeks later, on September 5, 1977. Despite launching later, Voyager 1 took a faster, shorter trajectory that allowed it to reach its planetary targets more swiftly. The Voyagers, despite potentially being overshadowed by modern inventions, were remarkable achievements of their era. They were equipped with advanced modules enabling them to study, record, and transmit data back to Earth. Packed with a variety of instruments, they analyzed atmospheres, magnetospheres, moons, and planetary rings. These tools included magnetometers, infrared and ultraviolet spectrometers, cosmic ray and charged particle detectors, and a sophisticated imaging system capable of sending detailed photographs of other planets in our solar system. Adding to the intrigue for those encountering the Voyagers for the first time, administrators included a golden record containing sounds and images. This record was intended to introduce potential extraterrestrial intelligences to humanity. The initial trajectories of the Voyagers were meticulously calculated for precision, taking advantage of a rare planetary alignment that occurs once every 175 years. This innovative approach allowed mission handlers to use gravity assists to accelerate the spacecraft and chart a course through the outer solar system. Voyager 2's journey included flybys of Jupiter and Saturn before proceeding to Uranus and Neptune. Voyager 1, following its close flyby of Saturn, was planned to veer sharply away from the ecliptic plane. It would approach Saturn's largest moon, Titan, renowned for its dense, nitrogen-rich atmosphere. Subsequently, Voyager 1 altered its trajectory toward its final objective, exiting the solar system and venturing into interstellar space. The scientists of the 1970s faced immense challenges in designing and sustaining the Voyager spacecraft with the technology available at the time. One of their primary concerns was ensuring that Voyager could operate for decades without running out of fuel. Unlike traditional propulsion systems focused on continuous thrust, Voyager 1 and its counterpart utilized a system of 16 hydrazine thrusters arranged in 2 sets of 8. One set controlled the spacecraft's orientation, while the other managed trajectory corrections. Hydrazine stored in tanks fed the thrusters through a network of pipes, where it decomposed with a catalyst to generate thrust, enabling precise navigation and instrument alignment. Another critical aspect was power generation. To ensure longevity and reliability far beyond the reach of solar power, both Voyagers were equipped with radioisotope thermoelectric generators. These devices convert the heat generated by the decay of plutonium-238 dioxide into electricity using thermocouples. Voyager 1 carries 3 RTGs, each utilizing plutonium-238 dioxide for its favorable 87.7-year half-life, ensuring a steady and reliable power source. Initially producing about 470 watts of electrical power, the output has naturally decreased over time as the plutonium decays. NASA manages this degradation by selectively shutting down non-essential instruments, such as cameras no longer useful in deep space darkness, to preserve power for critical operations. Despite reduced power output, essential systems remain operational, allowing NASA to continue receiving data from Voyager 1 and even updating its operating systems when necessary. This combination of innovative propulsion and power systems has enabled Voyager 1 to exceed expectations and continue its mission into interstellar space, far beyond its originally planned lifespan. The Voyager 1 started making returns on investment in terms of scientific knowledge early into its into-space journey. One of the ways it has enriched our knowledge of the cosmos was its flyby of Jupiter, which helped astronomers to see the jumbo planet in ways it had never been seen before. On March 4, 1979, NASA's Voyager 1 spacecraft took the first photos of rings around Jupiter. For example, astronomers were astounded when they realized Jupiter had rings. Before the flyby, nobody knew about the existence of the rings. However, Voyager 1 made a discovery of a thin, flat ring floating around Jupiter, proving that Saturn was not the only planet in our solar system festooned with rings. Voyager 1 detected more than rings. It returned a wealth of information about Jupiter's atmosphere. From the data and images returned, scientists were able to confirm the presence of complex cloud forms, swirling storms, and rapidly evolving atmospheric patterns. But one of the most iconic things Voyager 1 discovered on Jupiter was the Great Red Spot. It is actually a storm that has been blowing for centuries, and the storm is so massive it is larger than the Earth. Jupiter's red spot is a gigantic cyclone larger than the size of the Earth. Voyager 1 provided close-up images that showed us the intricate wave-like structures the storm is made of. In fact, the spacecraft allowed astronomers to take measurements of the storm, and they discovered that the Great Red Spot rotates counterclockwise. It also had a period equivalent to 6 Earth days. Another thing that astronomers discovered for the first time on other planets was lightning in Jupiter's atmosphere. It just didn't occur to them that lightning could take place elsewhere apart from the Earth. But Voyager 1 showed that the thunderstorms on the largest planet in the solar system were very similar to those on Earth. The thunderstorms on Jupiter are also formed from the heat rising from the interior of the planet. However, the lightning flashes were significantly more frequent and intense than what we see on Earth. It was the proof that astronomers needed that Jupiter has a dynamic and volatile atmosphere. Another discovery made by Voyager 1 on Jupiter was about the planet's magnetic field. According to the readings taken by Voyager 1, Jupiter has a magnetic field that is stronger than was hitherto estimated. In fact, it was by many dimensions more powerful than the Earth's magnetic field. This knowledge helped researchers to better understand the interaction of Jupiter's magnetosphere and solar wind and charged particles. For the first time, scientists realized that Jupiter's massive magnetosphere had huge swirling currents that were carrying charged solar particles. Voyager 1's exploration of Jupiter's moons, particularly Io and Europa, revealed unprecedented insights into these celestial bodies and reshaped our understanding of planetary moons in the solar system. As Voyager 1 approached Io, it captured images that stunned scientists on Earth. The spacecraft observed volcanic plumes erupting from the moon's surface, some towering up to 300 kilometers high, the first discovery of active volcanism beyond Earth. Among these, the most notable were from Loki Patera, a volcanic hotspot on Io. Infrared sensors aboard Voyager 1 detected intense heat emanating from these volcanoes. The spacecraft also revealed hundreds of volcanic calderas, some containing molten sulfur or sulfur dioxide, displaying vibrant colors ranging from yellow to green, black, and red. These findings underscored Io's status as a geologically active moon with a remarkably hot interior capable of sustaining such volcanic activity. Importantly, the material ejected from Io's volcanoes contributes to the ring encircling Jupiter, known as the Io torus, which interacts with Jupiter's magnetic field to create radiation belts and auroras around the planet. However, perhaps the most profound discovery about Jupiter's moons came from Voyager 1's encounter with Europa. The spacecraft's images of Europa unveiled a surface adorned with intricate patterns of crisscrossing lines, predominantly tinged with a reddish hue. Contrary to expectations, Europa exhibited relatively few impact craters, suggesting geological processes were actively resurfacing or erasing older features. This raised the tantalizing possibility that Europa's surface, though ice-covered, might conceal a subsurface ocean, the hypothesis supported by the moon's young, fractured ice crust and its potential internal heat sources capable of melting ice into liquid water. The prospect of liquid water beneath Europa's icy exterior has fueled speculation about the moon's potential to harbor life. If confirmed, Europa could rank among the most promising candidates beyond Earth to host microbial life forms. This hypothesis continues to drive scientific exploration and underscores the enduring legacy of Voyager 1's discoveries, which continue to inspire and inform our understanding of the solar system's diverse worlds. Voyager 1's exploration extended to Saturn about a year after its mission to Jupiter, where it uncovered further mysteries of the ring planet. One of its primary targets was Saturn's F-ring, a feature initially discovered by NASA's Pioneer 11 spacecraft the previous year. Voyager 1 also revealed that moons occupied the space within Saturn's rings, and it discovered several new moons previously unknown to astronomers. These moons included Atlas, Prometheus, Pandora, Rosalind, and Belinda. Among them, Enceladus stood out for its remarkable ability to reflect sunlight more brightly than any other object in the solar system, suggesting ongoing geological activity. Subsequent missions confirmed the presence of geysers on Enceladus, erupting water and ice particles into space, indicating the likelihood of a subsurface ocean. Looking forward, the future of Voyager 1 and its twin, Voyager 2, hinges on their power sources. The spacecraft are powered by radioisotope thermoelectric generators, which convert the heat from decaying plutonium-238 into electricity. Over time, the power output of these generators decreases as the plutonium decays. NASA anticipates a scenario where the RDGs may no longer provide sufficient power to operate the spacecraft and its instruments. Despite this inevitable decline, Voyager 1 will continue its trajectory through space indefinitely, venturing into realms no other human-made object may ever reach. It will remain a silent testament to human ingenuity and exploration, carrying with it a golden record of humanity's achievements and aspirations, even long after its scientific mission concludes. And that's it. Thanks for joining us on Spaceverse, where we journey through the cosmos with Voyager 1 and Voyager 2. From Jupiter's volcanic moons to the edge of interstellar space, we explore the universe's mysteries together. Don't forget to subscribe for more captivating space discoveries and cosmic adventures. See you next time as we continue our voyage through the stars.